Ever wonder how scientists predict something as complex as a plane's flight path, or the chaotic dance of weather patterns? Today, we're diving into a groundbreaking technique that turns messy, nonlinear systems into something manageable, using a tool called the Koopman operator. Let's break it down. Imagine you're watching a crowd at a concert. Individually, everyone's moving in different directions, but if you could map their movements over time, you might spot patterns. The Koopman operator does something similar for systems like weather, flight paths, or even molecular interactions. It's a mathematical magic trick that transforms complicated nonlinear behaviors into linear ones. Think of it as turning a tangled mess of ropes into straight lines. Here's the key idea. Instead of tracking every tiny detail of a system, the Koopman operator focuses on observables, features we can measure. For example, in a flight simulation, these might be altitude, speed, or angle. By applying this operator, we can predict how these observables evolve over time, even if the underlying system is super complex. Let's get concrete. Take a spring mass damper system, a classic physics problem. You've got a mass bouncing on a spring, with some friction slowing it down. Normally, you'd write equations for acceleration, velocity, and position. But the Koopman approach reimagines this as a state space, where each dimension represents a measurable property. By linearizing the system this way, we can use simple matrix math to predict future states. It's like using a spreadsheet to forecast the spring's next move. Now here's where it gets really cool. Researchers combined the Koopman operator with another method called HIPPO, which deals with time series data. Together, they created FlightKooba, a system that predicts flight trajectories by analyzing patterns in real-world data. Think of it as teaching a computer to read the language of flight, using math to guess where a plane will go next. They tested this on 2 datasets, one with real flight data from a Chinese aviation university and another with the Lorenz attractor, a famous example of chaos theory. The Lorenz system, which models weather, is notoriously unpredictable. Yet FlightKooba managed to spot hidden patterns, proving its power to tackle even the most chaotic systems. But how does this actually work? Let's dig into the math. At the core of these predictions are matrices n and m. Think of n as the system's natural rhythm, like how a pendulum swings on its own. M represents external forces messing with that rhythm, like a gust of wind pushing the pendulum. Together, they create a roadmap of how things change over time. Here's the genius part. Instead of recalculating everything from scratch every second, researchers save the middle steps of their calculations, like remembering the moves in a dance routine. Equations B15 and B16 act as their cheat sheet, letting them build predictions faster without losing accuracy. It's like learning to ride a bike. Once you get the hang of it, you don't need to relearn balancing each time. This approach is a game changer for long-term predictions. Small errors in flight path calculations, for example, can spiral into big problems. By optimizing these equations, tools like FlightKooba keep planes safe and on schedule. And it's not just about planes. Take CliMode, which blends physics with AI to forecast weather. By embedding real-world rules like fluid dynamics into its models, it's better at predicting extreme events. Then there's the Koopman operator, a mathematical magic trick that simplifies chaos. Think of a spinning top that's hard to track. This tool breaks its motion into simpler parts, making complex systems easier to predict. Even solar energy planning gets a boost. LSTM models, a type of AI, analyze cloud patterns like a detective solving a mystery, helping cities harness the sun more efficiently. These tools aren't just science fiction. They're solving real-world puzzles, safer flights, smarter energy grids, and more accurate weather alerts. The secret: combining data with the laws of nature to tackle systems too complex for traditional methods. So why does this matter? From safer flight paths to better weather forecasts, these tools help us make sense of the world's complexity. It's a reminder that even the messiest systems have order waiting to be uncovered, if you know where to look. Next time you board a plane or check the weather, remember, math is working behind the scenes to keep things on track. Thanks for watching. Hit subscribe for more deep dives into the science shaping our world.